So this is section 3.5, Summary of Curve Sketching. So it basically takes everything that you learned in pre-calculus about graphing, combined with the things that we've been talking about in calculus with the first and second derivatives, as well as asymptotes, and puts them all together to have you create the best graph possible of a function. So let's first think, without calculus, what can we use to sketch graphs? And things that we have, usually I have students give me their thoughts and ideas on this, but we can think about things like domain and range. Just by knowing information like that, it can tell us something about what the graph looks like, help us to critically think, hey, is my graph right? Intercepts as well. So x-intercepts, possible y-intercept, depending. Things even like symmetry. If you know that you have symmetry in a function, that can tell you, hey, if I know it looks like this over here, it's going to look like this over here, something like that. So remember that we have functions that are even, and if they're even, they are reflective over the y-axis. If the function is odd, it has reflection, again graphically, over the origin. And you could also have a function that is periodic, and that's all right about that, but for things that are like just sine and cosine, something like that, you know, if you know that, you know it should go on, you know, have a domain of all real numbers, things like that. And number 4 is asymptotes. And so for asymptotes, there's a couple different options. We could have a vertical asymptote, and that is of the form x equals a. So it's some vertical line at x equals some number that our function can never cross. And it is found by thinking about the limit as x approaches a. And for our function, so if you have plus or minus infinity, so that's telling you you have a function that's heading up or it's heading down right next to some vertical line. You could also have a horizontal asymptote, and these are all just possibilities. And that's going to be of the form y equals something like that. And you'd find that by looking at the limit, this is from one of the earlier sections, looking as the function approaches infinity or negative infinity, what's happening there. And if you are approaching some number, in this case b, then you have some horizontal asymptote at y equals b. And the last thing would be the possibility of a slant asymptote. So hopefully you learned about this in pre-calculus, but it's also known as an oblique asymptote, depends. And that's when you have an asymptote that's like a line that has a slope, and you know that's non-zero, and your function's approaching it, possibly up, possibly down. But it's found when you have rational functions, specifically that's the most common, where the degree of the numerator is 1 more than the degree of the denominator. So it's a line, y equals mx, you know, plus b, not the same b from before. And the thought of it, and this won't be a big focus, but you should just know about these from before, is if you look at a limit as you approach infinity or negative infinity, and the function minus whatever the line is, those are two y values there, I want you to see that. The difference between them is 0, so it's just if the function is approaching some line. Okay, so I mean there's a lot we can do without calculus, and with calculus we can just do a bit more. So what we've been talking about in previous sections is by using the first derivative we can tell when a function is increasing or decreasing. Okay. And of course that's going to be, you know, if your derivative is greater than 0, if your derivative is less than 0. Values where f has local maxes and or mins, So local maximums and local minimums, depending, of course, on where you have those horizontal asymptotes, horizontal tangents, excuse me. And then we talked about recently where the function might change concavity and has points of inflection. So that was one of the most recent things we talk about. So we put all those things together and we start graphing functions. So let's take a look at our first example, and we'll kind of do all these pieces here and just think about them. Not every function has every one of these pieces, but all of these things put together give us a good idea of what the graph of a function looks like. So here we have a curve. It is a polynomial of degree 3. And just by the fact that we know we have a polynomial, we know that it has a domain. That is all real numbers. Smooth and continuous, as I've said many, many times. The next thing we want to think about is intercepts. Now, this one's kind of interesting because a lot of you will say, oh, well, I know that the y-intercept is what happens if I let x equals 0. And so if I let x equals 0, then y equals -5, and we get the point 0, -5. So that's great. Okay. And on your graph, you could go ahead and write that down in your notes, put that point on 0, -5. I'll have it a couple slides from now. So after the y-intercept, we would want to think about the x-intercept, or x-intercepts, depending. And this is where students' pre-calculus knowledge comes in really handy, because you can probably look at that and say, well, it has 4 terms, and it doesn't look like I can, say, factor it by grouping. And so if there are any x-intercepts, they're just not easy to find, but it doesn't mean they don't exist. And so in a case like this, students have to think about basically the rational zero theorem or the rational root theorem. So you can go back and look at that if you need to. But that's what I would use here to see if there are any values that make this function 0, make the y value 0, because what we're trying to solve is 0 equals 2x cubed minus 9x squared plus 12x minus 5. We're trying to find the values that make that true. And again, those aren't simple. But if you remember the rational zero or rational root theorem, the idea would be you could think about the factors of the constant and the factors of the coefficient of the degree of the coefficient of the term of highest degree. And so that's going to be a 5 and the 2. And basically all the different possible rational roots or values that make this 0 have to be of the form p over q, where this is p and this is q. So possible p over q values are going to come from, and I should be a little more specific, all the values of p would be all the factors of 5, so that's 1 and 5, and q is all the factors of 2, 1 and 2. And again, I'm not teaching this, I'm just trying to remind people of it. But we also have to think about plus or minus, plus or minus, plus or minus, plus or minus. So the way that I would do something like this is I would think about taking each factor, so I'd go 1 over 1, so plus or minus 1. I'd go plus or minus 1 over plus or minus 2, so that's plus or minus 1/2. And then I would do the 5, so 5 over 1 is plus or minus 5. And then I would go 5 over 2 plus or minus 5/2. So again, rational zero theorem if you want to look it up, but it tells us that if there are any x-intercepts, they have to be any of these. These are the only options. That's what the theorem tells us from pre-calc. So what I would typically do is I would just throw in a value, and this is what I talk to my students about when I teach the class, is I would put in 1 and I would see what happens, or I would put in -1 and see what happens. And if that makes the function, the y value 0, then I already know that I have one of my roots and then therefore one of my x-intercepts. So if you try stuff, so for example, we put in 1, you can see that 1 would give us 2 minus 9, which is negative 7, plus 12, which is 5, minus 5, which is 0. So 1 works. So x equals 1 gives us y equals 0, and then we have one x-intercept of 1, 0. So you could go ahead and you could put that on your graph too. Then what that tells us is, and this might really take you back, but we could do this short division here, this synthetic division is what it's called. So this might really take you back, but it uses the coefficients of the function. And then we're basically just doing a division here. So again, this is supposed to kind of take you back to pre-calc, but I bring down the 2, I multiply, and then I add, and then I multiply, and then I add, and then I multiply, and then I add. And that tells me that my function can be factored into x minus 1, because 1 is my intercept. And then I lowered the degree on the polynomial by 1, and I would get this. So it tells me that my original function can be factored like this. And then I could see if it could factor more. And because, you know, I'm trying to find this out, and I did by saying that x equals 1. But then I would say, does it factor? If it factors, that'd be like really helpful to me, because then I'd have all of my, I'd have 3 roots. So I have 2x, I wouldn't put the 5 here like this, and that's going to give me 2, and that's going to give me 5, and I want both of them to be negative. There we go. So what it tells me is that I actually have 2 roots of 1. So I have 1, 0, and then I have another root of 1. And then I also have that x is 5 halves. And so that gives me my second intercept, 5 halves, 0. So 2.5, comma 0. So you could go ahead and you could put those onto your graph as well. So we have 2 intercepts, and we have a domain, and we have a y-intercept as well. And in terms of symmetry, I mean, this function is not even, it is not odd, and it's not periodic, so we're going to say no. In terms of asymptotes, well, we know it doesn't have vertical asymptotes, because as we head towards, well, there's no value for which, you know, you're going to head towards infinity or negative infinity, because these are smooth and continuous. Same thing with horizontal asymptotes. You're not going to have any issues with that, because as you know, we can think about as x goes to infinity here, y also goes to infinity, and as x goes to negative infinity, y goes to negative infinity as well. And the way to think about that is it's all about the leading term. So again, that's a pre-calculus knowledge. I'm using the idea about kind of limits here, but pre-calculus knowledge would tell us that because the leading term is what's you know, doing the most, when we put in a positive infinity to something like x cubed, that's still going to be a positive number. And if we put in, you know, as x goes to negative infinity, when we cube that, that's going to be negative. So now we can think about our first derivative here. And so that's increasing, decreasing, mins and maxes. So now we're actually getting to some calculus. So we take our derivative. You can pause if you want, of course. Okay, so that was pretty straightforward. And of course, we do want to know when this is equal to 0, because that's going to tell us something. So I liked the fact that it factored, because that's going to give me something kind of easy to deal with here. So we notice that in factoring we get that x is 1 and x is 2. So those are critical numbers. There's no place where the derivative is undefined. So these are our 2 values that we care about. And then I'm going to stick those onto a sign chart. So put my sign chart here, and these are the only 2 values that I need on it, x equals 1, x equals 2, And I just want to see increasing or decreasing. And when we talked about this in earlier sections, I did kind of a larger table, but you don't really need that if you don't want to. You can just kind of think about what's happening on the different sides of these numbers. So for something less than 1, I might pick 0. And when I put that into my derivative, you can see that you're going to get 6 times a negative 2 times a negative 1. So that's going to be positive. And then if we put in something like 1.5, we're going to get 6 times negative 1/2 times 1/2. And that's going to give us something negative, because positive, negative, positive. And then if I choose something bigger than 2, I'm going to see that I get positive, positive, and positive. Okay. So I've learned that my function is going to increase up till 1, and then it's going to decrease after that, and then it's going to increase again. So stuff I do need to know would be the y value, because these are points that I need. These are, we can see that this is going to be a local max, and this is going to be a local min. And so I need to know what the y values are. Now when I do the y value, I'm going to come all the way back to the original, because it's a y value on my graph, and so it can't go into the derivative. We know that it makes the derivative 0. We need to find the actual y value. So when we plug in 1, we actually get 0 in this case, but that is a valid point. And if we put in x equals 2, it looks like we get negative 1. So now we have 2 more points for our graph, 1, 0, and 2, negative 1. So you could go ahead and put those on your graph. And we now know that the function is increasing from 1 to 2. Nope, that's my opposite there. Oh, maybe I'll just change this. We know that the function is decreasing from 1 to 2. Everyone's like, that is not good. I do not like it. Yeah, looks a little weird. Okay, well, I just didn't want to, just wanted to stick with what I had. All right, so function is decreasing 1 to 2, and it's going to be increasing from negative infinity all the way up to 1, and then we'll union that with 2 to infinity. Okay, we're almost done, and then we can graph it. So make sure you have your intercepts on. Make sure you have your local max and local min on your graph. And then we just need the second derivative. And I mean, I used f of x, and I don't want to confuse people. This was given to us as y. So if that made you unhappy, I can try to make you happy again by changing those into y. So, and you know, y prime, so that you can say that it looks the same. So over here I'm going to do y double prime, and that's going to give me, because I'm going to take from my first derivative, 12x minus 18. So I've still got that idea of a factor of 6, so I'm going to pull that out, 2x minus 3, and that's going to give me 0, 2x minus 3, and I'm going to set that equal to 0 to get 3/2. As a possible point of inflection. So then I just do a quick check here with my second derivative, and I put on my 3/2 for x. And when I put in something less than 3/2, like 0, into my second derivative, I'm going to get negative. And so that tells me that I'm going to be concave down, and because down like brown, because we have a negative second derivative. And then after 3/2, so I put in something like 10, you're going to see that you get 6 times, you know, a big positive number in the derivative. And so that's going to be positive, and it tells us that after 3/2, we're going to be concave up. So I don't really need to do much more than that, except I do need to find out what this point is. So when x is 3/2, we can put that into the function, and it looks like, I did this because it's in the notes, we get a negative 1/2. And so we get the point 3/2, negative 1/2. Okay, so at this point, you're ready to graph. You have 5 points on your graph, 6 points actually, because well, some of them are repeats, but you've got kind of all you need to be able to then do a fairly good graph of this. And so you're going to have this value here, and this one, and this one's technically the same, but it's also, besides being an intercept, it's a local max, and we have this point, and then we have this point. So make sure you have all those on your graph, see if you can connect them, and then you're ready, when you're ready, move on, because on the next slide I have the graph. Okay, so here it is. So notice, I'll put some points in red. We have 1, 0, and we also have our 2.5, 0. These are our intercepts. And then notice that 1, 0, besides being an intercept, is a local maximum. However, we have 2, -1, which is a local minimum. So that's down here. Yep. Okay. And then we also had, you know, our intercept down here, so don't forget that point. And the other point, kind of this new and exciting point, is this point of inflection. So that was right here. That was at 1.5, comma, my point doesn't want to give me a point there, but that point right there is that exciting point that is the point of inflection. And notice that what happens on either side of it is that this function changes from being concave down to concave up afterwards. So that's kind of an exciting point because it's a very subtle point for the graph where, you know, you wouldn't be able to do that without calculus. You wouldn't know that that was the value without that second derivative. So things to not forget, this function does have arrows. I am showing that it's a polynomial, that it's going to go on forever. So you want to make sure you include that and everything else that we've done. And this is the graph of that polynomial. So what I'm thinking I'm going to do is maybe make a video for just each of the other graphs, because the rest of this section is just more examples of curve sketching. And typically when I teach this in class, I talk about this one and then I put students into groups and have them work through the other three while I walk around and see what kind of questions people have. So I would suggest trying to do any of the rest of them, following these steps, all these different 1 through 7 kind of things that we can look at and talk about, and kind of do as much as you can of any of them, and then watch the video, or maybe watch the beginning of the video and then try to do some on your own. But the more you can do on your own, the better off you're going to be. And you are going to, you know, need to be able to kind of produce this stuff for me on, you know, quizzes, exams, things like that. So see what you can do with the other ones, and then watch the videos to see if you got it right. So there you go.